Hey there, students! Welcome to today's exciting dive into the world of chemistry. Now, imagine this, you're baking a cake and you've got a whole bunch of tiny ingredients. What if I told you that, just like how we use cups or spoons to measure out our ingredients, chemists use something called the mole to measure the amount of substances? It's a little like a chemist's dozen, but this one is far more powerful. The mole is a way of counting particles like atoms and molecules, just as you would count eggs for your cake, but here we are talking 6.023 times 10 raised to the power of 23 of them in just one mole. Yes, that's Avogadro's number. Let's break that down a bit more. One mole of any substance will have exactly 6.023 times 10 raised to the power of 23 particles of that substance. This number helps us measure the tiniest things, atoms and molecules, in bulk quantities. So, whether it's hydrogen gas or a chunk of gold, when we say we have a mole, we are talking about the same number of particles, regardless of the material. Pause, isn't that fascinating? Pause, now let's dive deeper into Avogadro's number and how it helps us understand the incredible world of atoms and molecules. Now, let's dig a little deeper. What do we mean by atomicity? Well, atomicity refers to the number of atoms in one molecule of an element. For example, helium is a monatomic gas, it's made up of single atoms. But gases like hydrogen, oxygen, and nitrogen, they're diatomic, meaning they're made up of two atoms in a molecule. Picture this. When nitrogen reacts with oxygen, it forms nitric oxide, nitrogen gas plus oxygen gas nitric oxide, that's N2 gas plus O2 gas gives to no gas molecules. This reaction shows that one molecule of nitrogen contains two nitrogen atoms, which makes it diatomic. Just like when you have two hands, you can't have just one, nitrogen always travels with its buddy. This is why nitrogen, like oxygen, exists as a molecule made up of two atoms, and it's essential for understanding how gases behave when they react. Next, let's talk about the molecular formula of a gas. Have you ever wondered how chemists figure out the formula of a gas just from volume measurements? Well, it's all thanks to Avogadro's law. For instance, when hydrogen reacts with chlorine, you get hydrogen chloride gas, that's H2 gas plus Cl2 gas gives two HCl gas molecules. Notice something interesting here. Pause, hydrogen and chlorine are both diatomic, meaning they exist as H2 and Cl2 molecules. The beauty of Avogadro's law is that it allows us to deduce that for every two molecules of hydrogen and chlorine, we get two molecules of hydrogen chloride. That's how we find the molecular formula of a compound. It's all about the volume ratios. Now, let's connect molecular weight and vapor density. Did you know that molecular weight is closely linked to vapor density? Let's break it down. Molecular weight is just the mass of one molecule of a substance compared to the mass of one atom of hydrogen. Pause, but here's the key. Vapor density is the mass of a certain volume of gas compared to the same volume of hydrogen gas. By Avogadro's law, the molecular weight of a gas is twice its vapor density. Sounds a bit like a shortcut, right? So, if you know the vapor density of a gas, you can quickly calculate its molecular weight by just doubling the vapor density. For example, if a gas has a vapor density of 22, its molecular weight is 44. This simple relationship makes stoichiometry a lot easier when working with gases in chemical reactions. Let's connect the dots now. We know from Gay-Lussac's law that gases combine in simple ratios by volume when they react at constant temperature and pressure. Avogadro's law plays a big role here, too. Imagine you have one volume of hydrogen and one volume of chlorine gas. When they react, they form two volumes of hydrogen chloride gas, that's H2 gas plus Cl2 gas gives two HCl gas molecules. This law explains why gases react in such nice, simple ratios. It's like a perfect recipe. For every one volume of hydrogen, you get two volumes of hydrogen chloride. This whole number relationship is a beautiful example of how molecular volume is related to the number of molecules involved, and it's all based on the principles of Avogadro's law. Let's take a look at an advanced example. Suppose we have a gas with a vapor density of 22. How do we find its molecular weight? Well, using the formula from Earl, molecular weight equals to times vapor density. So, we multiply 22 by 2 and we get a molecular weight of 44. This tells us that the molecular weight of this gas is 44 g mol, which is exactly the molecular weight of carbon dioxide, CO2. It's like solving a mystery in the lab, and Avogadro's law helps us crack the case every time. To wrap it all up, Avogadro's law is more than just a scientific principle, it's a real-world tool for understanding gases. Whether we are determining atomicity, molecular formulas, vapor density, or even explaining Gay-Lussac's law, this law is the thread that connects all these ideas. And as we've seen today, it helps us make sense of everything from simple gas reactions to more complex calculations in stoichiometry. So remember, when you're looking at gases in chemistry, you're not just dealing with volumes and molecules, you're seeing Avogadro's law in action. I hope this session helped you connect the invisible world of molecules to the visible world around us. Catch you in the next class for more exciting chemistry.